Now let's calculate heat transfer or radiation heat transfer for diffuse and gray surfaces. Most enclosure encountered in practice involve non-black surfaces. Actually, in previous slides, we had an assumption that we can deal with the surfaces as black surfaces, but usually generally the surfaces are not black like what we have assumed. So usually we have non-black surfaces which allow multiple refraction to occur. So radiation analysis for such enclosure become very complicated because of those reflections or multiple reflections. Unless we find a way to simplify our problem solving by taking some assumptions. So we can assume that the surfaces of an enclosure are opaque or non-transparent material or surfaces. So we don't have any transmission or transmittivity through that transmittivity coefficient for that surfaces, and also we can assume that the surfaces are diffuse and gray. If you remember from the previous sessions, gray surface means the surface which the radiation which emitted from those surface is independent of wavelengths. And also we can assume that each surface of the enclosure is isothermal. In other words, the temperature at all of the points on the surface is equal. And also we can imagine or assume that both incoming and outgoing radiation, in other words emission radiation or receiving radiation, are uniform over each surface. So by this assumption, now we can calculate the radiation heat transfer for more realistic surfaces. For the normal surfaces, we have something like this with our assumption. A surface, as you can see here, which is opaque surface, no transmittivity of the radiation, and also as you can see here, the reflection is uniform, and so on. So this surface is according to the assumption in previous slide. Such a surface has its own radiation or emitted radiation due to the radiative radiation due to the temperature of the surface of the object, and also it will reflect the radiation which comes from the other radiation source, like the other object with different temperatures. So any surface will receive radiation and will reflect it, and also it will emit radiation due to its surface temperature. So the radiation energy of a surface is a combination of these two sources, reflection radiation and also emitted radiation, which, as you know from the previous sessions, the emitted radiation is equal to this much, and reflected radiation also is equal to this much, which epsilon and rho are the coefficient for the emissivity coefficient, and this one for the reflection coefficient. So surface emitted radiation as well as reflected, as I told you, the total radiation energy which leaving a surface per unit time and unit area. So per unit time and per unit area, total radiation energy is called radiosity, and we show that by J. So J, or radiosity, is actually is summation of these two radiation. And for a surface which we call the surface I, which is a gray surface and opaque surface, the emissivity and absorptivity are equal, and the summation of the absorptivity and reflectivity of the surface is equal to 1. So all of the incident radiation to the surface will be reflected, and also the emissivity of the surface will be added to that reflected radiation, and we will have finally this equation that total radiation from the surface is the summation of these two. So the Ji, or radiosity of the surface of I, can be calculated by this equation, which is the result of summation of radiation emitted by surface I, actually, plus radiation reflected by surface I. And radiation emitted by surface I is epsilon I EBI, or emissive power of the surface times emissivity plus irradiation of the surface multiple to the coefficient for the reflection. So by just some manipulation, and knowing this, we can write rho I as this equation. So from this equation we can find this one, these two actually. From these two equation we can find this rho I is equal to 1 minus alpha I, and alpha I is equal to epsilon I. So we can write this rho I as 1 minus epsilon I Gi. And it's the unit of radiosity is watt per meter squared. And for a surface which we can approximate as a black body, epsilon I, or emissivity, will be equal to 1, and we don't have any reflection. So for a black body, the equation which we have here, or the radiosity, will be equal to the emissive power of the surface, and simply we can write it Ji is equal to E of EBI, or emissive power of the black body of the surface I, and it is equal to sigma Ti power 4. Ti is the temperature of the surface I. So the radiosity of a black body is equal to its emissive power, as we have written here, since radiation coming from a black body is due to emission only. This comes from the definition of the black body. Black body is an object which absorbs all of the radiation which strikes to the surface. So we don't have any reflection for the black body. Then the rho will be 0, and we have only epsilon. Epsilon is equal to 1. Then to calculate the net radiation heat transfer to or from a surface, we should use this equation. Q dot I is the net radiation heat transfer, it may be from the surface or to the surface. It depends on the value of radiation to the surface, radiation energy to the surface, and from the surface. So this net radiation heat transfer is equal to radiation leaving entire surface I minus radiation incident on entire surface I. So for a general surface, for example this one with the condition I showed in previous slide, we have a radiation to the surface and radiation from the surface. The radiation leaving this surface I, will transfer heat from the surface by radiation, and radiation which incident on the surface will bring the actually thermal energy or heat by radiation to the surface. So we can write this equation. The net heat transfer is the difference between these two heat transfer actually. Then by substitution of these two, this is the radiosity actually, and this is the irradiation. We can have this equation. AI is the surface of the surface area or area of the surface. And by substitution of the Ji or radiosity and Gi as a black emissive power in the equation, we can rewrite it like this: Q dot I equal to AI, Ji or radiosity in that place, minus, instead of Gi we can write its value if we go to previous slide by using this equation actually. This is Gi. If we just manipulate this equation, Ji is equal to this. This is actually Ji equal to these terms. Then by substitution and rearrangement, we can, this is Gi. So by substitution Gi in the above equation, we can have this equation: Ji minus epsilon I ABI divided by 1 minus epsilon I, and which, if we just change the equation and bring out this term from that, we can write the equation, find this equation for the net radiation heat transfer. Actually, this is net radiation heat transfer, which is dependent on the emissivity of the surface, emissive power of the surface, radiosity of the surface, and area of the surface actually. And usually we call this term as a radiation heat transfer resistance actually. If we use electrical analogy, we can write this part as Ri, like this. This is the surface with the emissivity of epsilon I, with the area of the AI, and with the radiosity of Ji, and emissive power of EBI. Then Q dot I, or net radiation heat transfer, here from the surface, can be written by this equation. And if we just bring out this part as Ri, which is the surface resistance actually, surface resistance to radiation, we can rewrite that equation like this: Q dot I, rate of heat transfer by radiation from or to the surface, is equal to its emissivity power for black body minus radiosity of the surface divided by surface resistance to the radiation. which this surface resistance is equal to 1 minus epsilon I divided by AI epsilon I. You can see the resistance is dependent on or a function of epsilon or emissivity of the surface and area of the surface. And for a black body, this Ri is 0 actually, since epsilon I is equal to 1, then Ri become 0 for black body. So for black body, this resistance will be equal to 0 because the emissivity of the surface is equal to 1, and if we just put here 1 minus 1 will be 0. So total surface resistance to radiation will be 0. And Ji or radiosity and emissive power of the surface will be equal, or all of the radiosity of the surface is due to the emissivity or emissive power of the surface. And heat transfer direction can be also determined by the values of radiosity and emissive power of the surface. If the emissive power is bigger than radiosity of the surface, the heat transfer is from surface. And if the emissive power is lower than the radiosity, the heat transfer is to the surface. If we go back to the figure, also you can understand that this radiosity and different direction of the heat transfer. So by knowing the value of these two parameters, emissive power and radiosity, we can also determine if the heat transfer is to the surface or from the surface. And also some surfaces are encountered as re-radiating surface, which as you know, some surfaces are modeled as being adiabatic. Adiabatic means their backside actually are insulated. Their backside are insulated, well insulated, and the net heat transfer through them actually is 0. So the temperature of a re-radiating surface actually under a steady condition can easily be determined from the equation above once its radiosity is known. So we call this kind of surface re-radiating surface, which the backside of them is insulated, no heat transfer in this direction, all of the heat transfer is in this direction by radiation actually. Then if we are interested to know how much will be the temperature of the surface of for this kind of surface, actually the temperature at the surface is changing because of the heat transfer by radiation. Imagine here the heat transfer is only by radiation, so the temperature of the surface will change by change in the radiation, or due to the radiation heat transfer actually. This temperature can be found by this equation for such a surface. As I told you, radiosity is equal to emissive power, and it is equal to sigma Ti power 4, which sigma is the Boltzmann constant and Ti is temperature of the surface. So if we know if we know emissive power, if we know radiosity of the surface, simply we can find the temperature of the surface actually. So this is one way to find the temperature of the surface. And later we will see. So usually we may be interested to find the temperature of the surface due to the heat transfer by radiation actually, and we can use that equation. That one, the Q dot in previous slide was for the heat transfer from one surface actually. But in some cases we may have two different surfaces that we have a radiation, and then we may have a radiation heat transfer between those two surfaces. In such case, first of all, as I told you before, the heat transfer by radiation only happens if radiation from one surface strikes to another surface. So here we will add the view factor parameter to include this concept as well. If no radiation from surface I, for example here, strikes surface 2, then there is not any heat transfer by radiation between these two surfaces. Okay, so the net rate of radiation transfer from surface I to J, which we have radiation from surface I striking surface 2, or Q dot from surface I to J, is equal to radiation leaving the entire surface I that strikes surface J from in this direction, minus radiation leaving the entire surface J that strikes surface I. Simply, thermal energy or heat or radiation can be transferred or produced in the surface by radiation. From this surface to this surface, the heat is transferred by radiation. Also from this surface, heat is transferred to this surface by radiation, because from this surface also the radiation, which is due to the temperature of the surface, is actually emitted radiation energy comes to this surface as long as the radiation strikes this surface. So heat transfer in this direction is happening, also in this direction is happening. So finally the net rate of radiation heat transfer will be the subtraction between these two. So radiation leaving the entire surface I, radiation minus radiation leaving the entire surface J that strikes surface I. So we have something like this. If the heat transfer in this direction is bigger than this one, it means the total heat transfer direction is in this direction. Okay, then now you know about the direction, you know about the reason of this heat transfer. Okay, now let's just substitute the value. The radiation which leaves this surface and strikes to this surface is this much. The radiosity, as I introduced in previous slide, is the radiation energy from this surface, coming from this surface, which its surface area is AI. So this is radiation energy from surface out with the area of AI. How much of that will transfer energy to surface J? It is equal to the view factor from surface I to J. So AI Ji times Fi to J is the radiation, is this one actually, minus the radiation leaving the entire surface, this one in this direction, minus Aj J sub J F sub J to I in this direction. The radiation in this direction comes from this surface, then strike to surface I. So this is the main equation actually, the basic equation. Then by applying the reciprocity relation, we know that AI Fij is equal to Aj Fji actually. This is a reciprocity relation, we had that in previous slides. By knowing these and just put simply AI Fij, or simply put AJ Fji as AI Fij in this equation, we can bring out this term, this in Bau's equation. By using these two, we can find this one. So net radiation transfer between surface I and J can be written like this. Surface area of surface I, mu factor from surface I to J, times radiosity of surface I minus radiosity of surface J. And again, like usual, we can find radiation resistance for this configuration between these two surfaces by using analogy to Ohm's law for electrical current. So Q dot Ij is equal to Ji minus radiosity of surface I, radiosity of surface J divided by Rij. Rij is the radiation resistance between the two surfaces, or we can call that space resistance to radiation. This is space resistance because it's between two surfaces, which this Rij is equal to 1 divided by AI Fij. So the space resistance is dependent on the surface area of the emitting surface and the radiation emitting surface and the mu factor from that surface to the other surface. That one was for two surfaces only. When we have numerous surface, actually more than two surfaces actually, then the radiation from surface I will transfer heat to other surfaces by radiation, as long as the radiation from that surface strikes the other surface. Usually this happens in the enclosure, and because there is different surfaces and all of the radiation will strike to the surface itself or other surfaces. In this case, simply it is the radiation, the total rate of heat transfer is equal to the summation of heat transfer from that surface to the each one of that the other surfaces by radiation actually. So this is the previous equation in previous slide, but we should write this equation for all of the surfaces from surface 1 to surface n. Then our equation will change to this one. This is for radiation heat transfer for an enclosure with n surfaces. Now, up to now you have already know about how to calculate the heat transfer from the surface between two surfaces according to the mu factor and also the surface temperature. Usually in the problem encounter radiation heat transfer, we may ask to find the temperature of the surface due to the radiation heat transfer, or we have to find the net rate of heat transfer by radiation, which for the surface which their temperature is now. So When the surfaces with a specified net heat transfer rate or Q dot is known, we can use this equation to find Ji or other parameter or radiosity or vice versa. And for the surface which we know their specified temperature, or for the surfaces which their temperature is given, we can use this equation to find Ji actually, for example. Each one of these parameters can be unknown, but usually the nature of the problem encountered radiation heat transfer is one of these two. And as you can see here, we will have a set of equations in terms of the number of the surfaces. In each one of these two methods, we will have n different equations that can be used to find different parameters like heat transfer, rate of heat transfer, or radiosity of the surfaces. And it can be used to find heat transfer for each surface, for example. And if we have n surface, we will have n linear algebraic equations that can be used to find that those n unknown radiosity, for example, for n surface enclosures. And when this radiosity is given, in other words, when we have J1, J2 until Jn, the unknown heat transfer or unknown surface temperature can be determined by these equations. If we know J for all of the surfaces, this Q dot or Ti can be found by these radiosity or Ji and J sub J. And to solve these n equations, we can use two different methods. The first one is direct method. In this method, is based on the equations which we have, and we can find the n unknown parameters directly from the equations. And we have also network method. As I show you, network method means using this R, these equations actually. When we have less than 4 surfaces, so when we have 3 or even 4 surfaces, we can use this method, this network method, to find the unknowns, which can be transfer or temperature of the surfaces. But when we have more than that, the number of surfaces is more than 3 or 4 surfaces, we should use direct method and use these equations instead of using the radiation resistance or space resistance. Okay, so by this slide we reached end of this chapter, and our discussion is finished about the radiation heat transfer. Thanks for watching and have a good time.